explained with the help of probability density function, and from the probability density functions we can explain the continuous distributions. And there are three continuous distributions, there are four continuous distributions. One we are already covered, I think, exponential distributions and uniform distribution. I think in the last sessions which we are cleared these two distributions, exponential distributions and uniform distributions. Okay. Now there are two more continuous distributions. One is Gaussian distribution and another one is Rayleigh distribution. Okay. Now these two which we already finished, now we'll see the Gaussian distribution. Okay. Now Gaussian probability density function, because all continuous distributions are explained with the help of the probability density function, right? So this is the Gaussian probability density function. The Gaussian probability density function, which is good for complete mathematical analysis for all the random signal process. 1 by 2 pi 1 by root 2 pi sigma x square e power minus of x minus mx whole square by 2 sigma x square. Now this is a Gaussian distribution which is a function of mean and variance. This is a Gaussian distribution which is a function of mean and variance. Now where mx is a mean of a random variable x and sigma x square is a variance of a random variable x. Now this is the Gaussian probability density function which is a continuous distribution which is a function of mean and variance. Okay. Now we will try to write the distribution function. Now let us take let us assume some k equal to 1 by root over 2 pi sigma x square. Now see here, this is the random variable x. I will see the probability density function fx of x. Okay. Now when x minus mx is equal to 0, which means at x equal to mx, at mean at x equal to mx, what happened? If x equal to mx, now this is 0 e power 0 1, now 1 into this is 1 by 2 pi root. Therefore when x equal to mx, when x equal to mx, fx of x is k. When x equal to mx, fx of x equal to k. X minus mx, which is equal to sigma x, x equal to mx plus sigma x. When x minus mx is equal to sigma x, this is sigma x square can cancel, so e power minus 1 by 2. So this is nothing but now k into e power minus 1 by 2. But what is the distance from mx? So the distance from mx is sigma x, because the centered value is mx. Now, so fx of x which is equal to k into e power minus 1 by 2. Now, x minus mx, which is equal to 2 sigma x, which is nothing but x equal to mx plus 2 sigma x. So therefore, fx of x, which is equal to k into, this is 4 sigma x square cancel 4 by 2, 2, k into e power minus 2. Now this is 2 sigma x, which is distributed from mx. So now if you consider all these points, now this is the Gaussian probability density function. Now see here, now there are major important points we can identify from this. Now this is the distribution, forget about the distribution, but any distribution whose centered value is nothing but mean. Then there is a definition of mean. What is the definition of mean? Mean is mean or average value or first movement of a random variable where a distribution is centered. Mean is a measure of where the distribution is centered. Any distribution whose centered value is nothing but the mean. And one more thing, the spread of the distribution, see here, this is the spread of the distribution about its mean. The spread of the distribution about its mean is called as variance. Spreading, how much is the spread of the distribution about its centered point, about its mean, is called as variance. Variance is the spread of the distribution about its mean. Therefore, this is the probability density function, which is a continuous distribution, which is a Gaussian distribution, now which is centered at mean of mx. A spread of the distribution about its mean is called as variance. In one GATE examination, one bit is like this. Now these are the two questions which is given, and in the options, variance of figure 1 which is equal to variance of figure 2, variance of figure 1 which is greater than variance of figure 2, variance of figure 1 is less than variance of figure 2. Now variance of figure 1 and variance of figure 2 both are 0, like that the options are available. So how you can decide it that? Now what I am doing is, any distribution whose centered value is mean, now from the center how much is distribution is called as variance. So now see here, this is the spread of the distribution about its mean is called as variance. Variance of figure 2. Now this is the spread of the distribution about its mean is called as variance. This is variance of figure 1. So you can easily identify. Now variance of figure 2, variance of figure 2 which is greater than the variance of figure 1. Clear or not? Now this is the distribution whose centered value is mean, and spread of the distribution about its mean is called as variance. Note down. Okay. Now I am asking same Gaussian probability density function now with mean equal to 0. If Gaussian distribution function with mean equal to 0 means what? If it is a Gaussian distribution function with mean 0, what is the meaning of that? What you can understand? The Gaussian distribution with mean equal to 0 means now the distribution whose centered at 0. Now this distribution curves are shifted to origin side. Because any distribution whose centered value is nothing but mean. Now fx of x, which is equal to 1 divided by root 2 pi sigma x square e power minus x square by 2 sigma x square. Now this is the Gaussian probability density function with mean equal to 0, which means now the distribution whose centered at origin. Now the distribution which is centered at origin with mean equal to 0. Now this is the probability density function . This is the probability density function which is centered at mean equal to 0. Now see here, this is also the distribution whose centered value which is nothing but mean which is equal to 0. Okay. Now this is the Gaussian distributions, which is one of the continuous distribution, and another continuous distribution which is nothing but Rayleigh distribution. Rayleigh probability density function. Now what is the Rayleigh probability density function which is similar to the Gaussian distribution? Now the Rayleigh distribution which is similar to the Gaussian distribution but only for positive values of x. But this Rayleigh distribution which is only for the positive values. The difference between a Gaussian distribution and Rayleigh distribution, the Rayleigh distribution which is similar to the Gaussian distribution but only for a positive values of x. Okay, no. So this Rayleigh probability density function which is similar to Gaussian distribution but only for positive values of x, only for positives. These are the continuous distributions. Okay. Then you ask one question, sir, what is the use of this continuous distribution? Now your main aim is to study the random signal theory concept. For the purpose of what? The main aim to study the concept of random signal theory for getting a mathematical shape of a noise signal. Is it right or not? Because the noise signal which is continuously varying with respect to time, you cannot predict, it is a random signal. So for such kind of a random signals, I want to represent it some mathematical values for that, some mathematical equations for that, some predictable values for that, some properties for that. To have a properties of that particular noise signal, we have all these particular random signal theory concept now, which is mean, variance, mean square value, continuous distributions, Gaussian distribution, all these also useful to have a shape of a random signal, sorry, noise signal. Okay. Now at the end you can understand now what is the use of studying all these things, now where we can utilize all these things to explain the behavior of the noise signal. Okay, now we'll see. Now so far what we are doing is a random signal theory. Is it right or not? Random signal theory. Now if a random variable x, we call it as x, if a random variable x is a function of time, if a random variable x is a function of time, is called as random process, is called as random process. Now may represent it like this: random variable is x, random process is x of t. Now my question, the random signal theory concept is for the purpose of explaining the behavior of the noise signal, then keep that particular point in your mind and you tell me a noise is a random variable or a noise is a random process. You tell me. Okay. You know that because the noise voltage, let us take this is the noise voltage. The noise voltage which is continuously varying with respect to time. Am I not? We cannot predict how much is the noise at this particular instant of time. The noise voltage is a random process. The noise voltage is a random process, is a function of time, because we cannot predict how much noise at this particular time. Okay, a temperature of a city is also a random process, not a random variable which is continuously varying with respect to time. Okay, this is a function of time. So therefore a noise is not a random variable, the noise is a random process. Okay, now before we start studying the random process which is functional, see again I cannot explain what is mean, variance of random process. Now previously you are saying mean of a random variable x, variance of a random variable x, mean square of a random variable x, like this. This is the random variable theory. Now what is a random process concept? Mean of a random process, mean of a random process, variance of a random process, mean square of a random process. Same formulas and everything will be same, but these are the functions of time, which is a random variable which is a function of time. So it is called as a random process. That is the only difference. Okay. So now in this particular random process concept, then we'll see two important. Now here one is autocorrelation function and another one is autocorrelation function, another one is power spectral density. These two are interlinked, then we can first study this. Okay, autocorrelation function. What is the meaning of autocorrelation function? A signal, let us take this is a random process, right? So not x of t. A signal x of t, again compare the same signal with itself. A signal, compare the same signal with itself and find any similarities between these two signals is the process of autocorrelation function. Then you ask one question, sir, I just stand in front of a mirror and the image which is appear on the mirror and me, what are the similarities? Can you find any similarities? Because the same image which we can appear on the mirror. So in the same concept here, a signal, compare the same signal with itself and what should be the comparisons and similarities between these two signals means is not a correct question. Okay, now it's not a meaningless question, because it is the signal comparing with the same signal, both are same. So therefore both are same means I want to have a properties, features, similarities. That's why I can do like this. A signal, this is the autobiography, right? Your own biography you can write, that is called as autobiography. So a signal, compare the same signal with itself, autocorrelation. A signal compare with another signal, cross correlation, like this. Okay. Now a signal compare the same signal. Sir, how can I compare? Because both are same. So you can compare like this. Take a signal and compare the same signal with a delayed version or with an advanced version with some variable tau. So you compare the signal with a delayed version or advanced version of the same signal and find any similarities. Now that is the process of autocorrelation. That is the process of autocorrelation function. Understand or not? Okay, now that we will see. Now autocorrelation function represented by Rxx of tau, which is a random process x of t. Compare the same random process with advanced version or with delayed version, x of t minus 2. Okay. Now which is nothing but Rxx of tau, which is equal to integral minus infinity to infinity x of t plus tau. This is a first movement of a random process. Therefore x of t dt, or which is integral minus infinity to infinity x of t minus tau fx of t. This is a function of time. Now we will find the similarities. Now we will find what is the first similarities. Now for finding the properties of the autocorrelation function, let us assume this is thus probability density function is, let us assume this fx of x equal to 1. Okay, let us assume a probability density function is a uniform distribution of, because the area under the probability density function, you know that the area under the probability density function is 1. So for comparison purpose, let us assume this fx of t which is equal to 1 for finding a comparison. Okay, for finding the formulas you should keep this. Okay. Autocorrelation function at origin. Autocorrelation function at origin. Now see here, autocorrelation function at origin, which means at tau equal to 0. Autocorrelation function at origin, which is nothing but Rxx of tau equal to 0, which is equal to integral minus infinity to infinity x of t into x of t dt. So what is the meaning of that? Autocorrelation function at origin, which is nothing but, whether you substitute here or here, same answer, right? Autocorrelation function at origin, which is nothing but, this is nothing but the energy of the random process or not? Energy of a random process x of t. What is energy? Energy is nothing but a maximum value or not? Now, which is nothing but the maximum value of a random process x of t. Autocorrelation function at origin, which is nothing but the maximum value of a random process, and which is equal to the energy of the random process, and energy of the random process x of t. So the maximum value of autocorrelation function occurs at origin. Okay, the maximum value of autocorrelation function occurs at origin. Now this is the first similarity, and the second similarity is, if you observe, now Rxx of minus tau. Substitute minus tau here, it will become here. If you substitute minus tau here, it will become like this. So whether you substitute here, you can get this. If you substitute here, you can get this, which is nothing but Rxx of minus tau, which is equal to Rxx of tau, which is nothing but autocorrelation function is an even function of tau. Autocorrelation function is an even function of tau. This is the autocorrelation function is an even function of tau. Now, the maximum value of autocorrelation function occurs at origin. Therefore, Rxx of 0, which is always greater than Rxx of tau, because the maximum value you can get at the origin, then that value which is always greater than Rxx of tau, as tau increases, then Rxx of tau is decreases. The meaning of that is, as tau increases, you can find a more similarities between a signal and the same signal with itself. Now let us take, for example, then you take a photograph of your image right now at the age of this. Then after 10 or 20 years, you can take another photograph, compare the same two photographs. You can have a more similarities or not. You can get a more comparisons or not. You can get more differences or not. So as time increases, as tau increases, differences between the signal and the same signal, now you can get a more similarities, because as time increases. So you can get the maximum value at origin, and you can get a more differences as the time increases, obviously. Okay. Now this is the properties of the autocorrelation function, and the maximum value of autocorrelation function occurs at origin, and autocorrelation function is an even function of tau, and autocorrelation function is a maximum value at origin which is greater than this tau. As tau increases, this value is decreased. Okay, no doubt. Here you can have one relation, right? You can have one more relation. Autocorrelation function at origin, which is nothing but, if you take here expectation of, what is this? Expectation of x square of t, means autocorrelation function at origin is nothing but mean square value of random process x of t. Autocorrelation function at origin is nothing but mean square value of a random process x of t. Mean square value of a random process is nothing but total power of a random process x of t. Am I not? The mean square value is nothing but the total power of a random process x of t. So can I take a relation here? I'll find one relation continuously in our notes is also available. When mean equal to 0, when mean of a random process is equal to 0, you know the first relation. What is the first relation? Variance of a random process which is equal to mean square of a random process, because variance equal to mean square value minus square of the mean is 0, right? Variance equal to mean square value is the first relation, and the second relation is now variance of a random process which is equal to mean square of a random process which is equal to, what you are getting, which is equal to autocorrelation function at origin. Autocorrelation function at origin. Okay. Now we will see the power spectral density. Power spectral density. Now I'll take, for easy explanation, I can take one small example here. Now this is a two-sided power spectrum. This is a two-sided power spectrum. Now this is the two-sided power spectrum. Now see here, this is actually the Fourier transform of train of rectangular pulses. Now this is the rectangular pulses train. Then for that rectangular pulses train, if you do the Fourier transform, now this is the Fourier transform of train of this particular rectangular pulses. Okay, I don't take that Fourier transform of the rectangular pulses, all these things. I just take one simple example to study the operation of power spectral density. I just take this one case directly. This is the two-sided power spectrum, which is a Fourier transform of a train of rectangular pulses. Now see here, now this is the two-sided power spectrum, which is a Fourier transform of train of rectangular pulses. Now see here, now this is power versus frequency. This is the power spectrum. I am writing power spectrum because this is the power versus frequency. Sir, which power? V square by R or I square into R is power. But here I just take only V square, means R equal to 1. Therefore, this power is nothing but normalized powers, right? Normalized powers. So these are the normalized powers distributed over the frequency range. Therefore, this is a two-sided power spectrum. I just take a two-sided power spectrum, okay, which is actually the Fourier transform, which is the Fourier series, not Fourier transform, Fourier series of this train of rectangular pulses. Okay. Now see here, what I am doing is I just add these normalized powers over a particular duration. Okay. Now let us take, I just add some of the normalized powers. Let us take over duration. Now this is V0 square, this is V0 square plus V1 square. Now this is V0 square plus V1 square plus V2 square. Now and so on. Okay. Now I just take over a frequency range, over a certain frequency range, I just add this sum of these normalized powers. Now which is nothing but, see here, sum of the addition, sum of the normalized powers, sum of the normalized powers over a certain frequency range is called as power spectral density, is called as sum of the normalized powers over a certain frequency range is called as power spectral density, represented by S of f. Now this is the power spectral density, sum of the normalized powers over a frequency range. So units are power means watts, over a frequency range means hertz. Power spectral density units are watts per hertz. Sum of the normalized powers over a certain frequency range is called as power spectral density. Now see here, the power spectral density S of f, which is equal to sum of the normalized powers over a frequency range, is called as power spectral density. This is watts per hertz. Sum of the normalized powers over a certain frequency range is called as power spectral density, watts per hertz. Note down. Clear or not? So from here you can write like this. So S of f, which is equal to sum of the normalized powers over a frequency range, is called as power spectral density. This is the power spectral density. Units are watts per hertz. Now dP, which is equal to S of f into df. integrate both sides. Integration of dp, which is nothing but p, integration s of f df. Now area under power spectral density. Now what is this? This is area under power spectral density. Area under power spectral density. Area under power spectral density is called as power. Area under power spectral density is called as power. Now this is the, if you want a power, integrate the power spectral density. Okay. Now area under the power spectral density is called as a power. Now see here. So can I write like this? The power spectral density from this example. What is the power spectral density definition? Sum of the normalized powers. Sum of the normalized powers over a frequency range. Sum of the normalized powers over a frequency range. Sum of the normalized powers over a frequency range is called as power spectral density. Sum of the normalized power over a certain frequency range is called as power spectral density. Okay. Now from here we will have one important relation which is very useful for studying the noise analysis. Now this is a, let us take a filter. A filter whose impulse response is h of t and frequency response is h of f. Now this is the filter output. Signal is V0 of t. Filter input signal is Vi of t. This is input signal to the filter. This is output signal. This is input signal and this is output signal. Now Vin, this is spectral amplitude. Spectral amplitude. Spectral amplitude corresponding to input signal. Now this is V0n. V0n. Similarly, the spectral amplitude corresponding to output signal. This is spectral amplitude corresponding to output signal. The spectral amplitude corresponding to input signal. Now let us take one simple example here. What is the relation between these signals and an impulse response of the filter? Now V0 of t, which is equal to Vi of t convolved with h of t. This is convolution in time domain, which is nothing but multiplication in frequency domain. Vi of f into h of f. Now this is regarding the signals, but what about the spectral amplitudes? Now the spectral amplitudes is nothing but the output spectral amplitude, V0n. Now the spectral amplitude at output side, V0 output voltage equal to gain multiplied with input voltage. So the spectral amplitude at the output side, which is nothing but spectral amplitude at the input side multiplied with gain. Right? So now I am asking one question. Now here power spectral density of the input signal is Si of f. Power spectral density at the output of the signal is S naught of f. Now, what is the power spectral density at the input of the signal Si of f, which is equal to power spectral density at the input of the signal, which is equal to summation n equal to minus infinity to infinity Vin square into delta of f minus n f naught. Now this is the power spectral density at the input of the input signal. So this is the power spectral density at the input signal. Vin is the spectral amplitude corresponding to the input signal. Similarly, can you please tell me what is the power spectral density at the output signal S naught of f, which is equal to summation this one. Similarly, summation n equal to minus infinity to plus infinity. Sum of the normalized powers at the output signal is V naught n square into delta of f minus n f naught. So can I write like this? This is the power spectral density at the output side. The power spectral density at the output side, which is nothing but summation n equal to minus infinity to infinity. What is the power spectral density at the output signal V naught n? Can I substitute here? What is V naught n? V naught n, which is equal to h of f into Vin whole square into delta of f minus n f naught. Therefore, power spectral density at the output of the signal, which is equal to summation n equal to minus infinity to infinity Vin square into delta of f minus n f naught into h of f square. Power spectral density at the output of the signal, which is equal to power spectral density at the output of the signal, which is nothing but now this is nothing but the power spectral density at the input of the signal is nothing but Si of f. Therefore, what is the relation? This is a very important relation throughout the noise behavior. Now what is that? The power spectral density of the noise, the power spectral density at the output of the filter, which is nothing but power spectral density at the input of the signal multiplied with square of the filter impulse response and square of the filter transfer function. Okay, this is very important. A power spectral density at the output of any filter, which is nothing but the power spectral density at the input of the filter multiplied with square of the frequency response of that particular filter or square of the transfer function of that particular filter. Okay, note down. Right now, the power spectral density, which is nothing but relation between power spectral density and autocorrelation. Power spectral density, which is nothing but Fourier transform of autocorrelation function, and autocorrelation function, which is nothing but inverse Fourier transform of power spectral density. Right now, let us see here. Power spectral density S of f, which is equal to integral minus infinity to infinity autocorrelation function Rxx of tau e power minus j 2 pi f tau into. Now, autocorrelation function Rxx of tau, which is equal to inverse Fourier transform of power spectral density into e power plus j 2 pi ft df. Now, at zero frequency, f equal to 0. At zero frequency, s of 0, which is equal to integral minus infinity to infinity rxx of tau f equal to 0 e power 0 1 into d tau. What is the meaning of that? At zero frequency or at DC frequencies, the power spectral density at zero frequency is nothing but area under autocorrelation function. Is it right or not? Power spectral density at zero frequency is nothing but area under autocorrelation function. Now similarly, come to here, second one, autocorrelation function at origin. Autocorrelation function at origin, which is nothing but tau equal to 0. Autocorrelation function at origin rxx of 0, which is equal to area under t equal to 0. Autocorrelation function at origin tau equal to 0, 0. So, what is the meaning of this? Autocorrelation function at origin, which is nothing but area under power spectral density. What is the area under power spectral density? Area under power spectral density is nothing but power. The same thing or not? Autocorrelation function at origin, which is nothing but area under power spectral density, or a mean square value or a total power, both are same. Right? Now, the power spectral density, this is a power over a frequency range. Practically all are positive frequencies. So, power spectral density is always positive. Is always positive practically. Okay. Now, is always positive. Now, we have one relation here. Now, let us take that relation also. Now, what is the third relation? Now, the third relation here, mean square of a random process, which is equal to variance of a random process, which is equal to autocorrelation function at origin, which is equal to autocorrelation function at origin, which is equal to area under power spectral density, area under power spectral density, area under power spectral density, which is equal to area under power spectral density, which is equal to the total power. All are same when mean equal to 0. All these are the relations when mean equal to 0. Now, this is the power spectral density and autocorrelation function relationship.